Welcome. If you're in my class, you have already done an activity in which we addressed a question sort of like this. This question here is sort of introduces this unit. And the question is, does walking 10 miles always take you 10 miles? Well, as will be the case in a lot of instances in this class, that's not a simple question. Or there isn't a simple answer. There isn't a straightforward answer. Many answers in this class could most appropriately start with, well, that depends. Your job, if you're in my class, for when you come back next time, is to have a couple of answers to this. In one case, you should be able to describe a case like this. Well, it does. Walking 10 miles, maybe not always, but let's get rid of this. It does take you 10 miles. Like when you'll fill in, you'll complete that phrase. But you could make an argument, I would bet, that says, well, it doesn't. Walking 10 miles doesn't always take you 10 miles because, sorry, pardon my slang, because, well, like in this situation, so do your best when you come back next time if you're in my class to describe a case in which walking 10 miles does take you 10 miles, or a case where walking 10 miles doesn't take you 10 miles. Okay? Yeah, good start. All right, and the question is, a bigger question for this whole unit and a lot of this year is, what else works this way? What else, maybe, especially if you're thinking about this answer, a case where, well, walking 10 miles, when you do it like this, doesn't really take you 10 miles. What else works that way, and what's the common thread that we really have to take into account? Well, that common thread, come on now. That common thread is the difference between what we call a vector and a scalar. All right, every quantity, everything we can measure, every quantity in the universe that can be measured is either a vector or a scalar. All right, scalars, thinking it's a scalar includes only magnitude. And magnitude means size, numerical amount, value. All right? But there's a whole class of quantities that are called vectors. And those include not only a magnitude, but also direction. All right, there's a whole ton of quantities that it makes perfect sense to say, well, an amount of something and then say north. Like, for example, 10 miles north. Well, there's nothing strange about saying that. And so, well, we could say, like, yeah, I'll put that over here. Yeah, so if we say, 10 miles north, well, there's a name for that, and unfortunately the name's not, it sounds like a distance, doesn't it? But we don't call it a distance in this class. I'm going to call that, a change in position. That's one example. Now, if we just said 10 miles, it's fine to say 10 miles, right? We don't have to assign what direction we're talking about. If we just say 10 miles, well, that makes this what we're used to, a distance. An example over there. So notice this vector quantity, change in position, has a scalar part, and it has a direction part. So the scalar part is the size of it, the numerical amount of it, the numerical value. okay? There are lots of these things. There are some things where it just doesn't make any sense at all to ever say north or south or up or down or east and west. It just wouldn't make any sense. Like you say, how long you spend on that homework last night? I spent like 3 hours west on it. Well, no, it doesn't make sense, right? So 3 hours, you couldn't add a direction to that. It wouldn't make any sense. Now, could you say I drove for 3 hours north? Sure, but the 3 hours part, the amount of time, that's an amount of time, right? So if we say 3 hours, well, by itself, that's a scalar. Time's a scalar. There's no direction associated with time. I hear you smart guys out there and girls say, well, doesn't time always go forward? Yeah, forward's not a spatial direction. We're talking about spatial directions. Okay, there are lots of these things, lots of these things. What I'd like you to do also is try to come up with some more examples. Now, a note about this sort of thing. Some of you will just go to the internet and just Google it. If you're that guy or girl, be my guest. All right. If you're up for a little more of a intellectual challenge, think and see what you can come up with. You will not be thought of as brighter, dumber, dimmer, or better or worse if you come in tomorrow and say, well, I thought and I came up with 1, or someone says, oh, I Googled and I got 10. I'd rather have you think and come up with 1, okay? But I'll leave that there. But I'd like you to see if you can come up with some other stuff, both like what would the measurement look like? What would you call it? What would you say? And then what do you call that? All right? What would you say and what do you call that? All right, so you can come up with. You'll find a few as we go on in this video, but yeah, let's go forward. So, vectors. What we're concerned about is being careful about things where direction really matters, where there's a numerical, measurable quantity, but the direction that quantity has matters a lot. And then luckily there's a real easy way to make a simple drawing that represents a quantity of a certain numerical size and that points in a very specific direction. And gee, what's that super complicated drawing? Well, here it is. Look, it's a vector. We did vectors in math. Awesome. There's a vector. All right, this vector has 2 important parts. This is called the tip. This is called the tail. Not the tall, the tail. Tail. Yeah, so, but, as we said here, there's lots of different kinds of vectors. Hopefully you've already come up with, I should recommend that you pause here and come up with a few more. So is this a change in position vector? Or is this some other kind of vector? Well, how do you tell? Well, you have to have some sort of scale. Because the length of this vector, length of drawing, the length of the graphical vector, well, I should say is proportional to, if we do this right, is, proportional to the vector's magnitude. All right, so you have to choose a scale. Like, for example, if I said every centimeter of this vector's length represents 50 meters. Well, meters is a measure of distance. So that would mean this is a change in position vector. Well, and how do I know what's this? What direction does that mean? Up and to the right on my paper. Well, I could do something like, so what I also want to do is directional orientation. Like, for example, what if I mean, well, I don't know, in some sort of crazy layout, I might mean that this way is north, south, east, west. And I could say, okay, well, I guess what I mean by this is that this thing points, so I don't know, what's the, some number of degrees west of north. And so by drawing this, I could say, well, all right, every centimeter of this thing's length represents 50 meters. I don't know how long this looks like it is on your paper, but you measure it with a ruler, you make a little proportion, you say, oh, okay, I guess that represents 275 meters at some angle 38 degrees west of north. Okay, well now I could get from somewhere to somewhere else based on this scale drawing, this vector drawing that you've made. Okay? However, right, these drawings don't always have to represent how far to go in a certain direction because there are lots of different vector quantities. Okay? This is going to be a little bit tricky to do, but what I say is here, you do this one. I actually want you to do both of these because I can't really do it on the big screen here unless I'm not going to do it in the big screen, but I want you to come in tomorrow if you're in my class. Next time I see you, I want you to have both of these done, and here's how you do it. All right? You choose a scale, and that scale is going to be something, it's going to be 1 centimeter equals some number of somethings. In this case, it's going to be some number of kilometers. In this case, it's going to be some number of meters per second. So I guess the question is, what kind of vector is this? If it's something measured in meters per second. This one we sort of know, right? This is kilometers, a measure of distance. Meters per second, a measure of what? But the nice thing is, we can still draw a vector B that is still an arrow, but it represents a completely different kind of quantity than vector A that we can also represent with an arrow. Because both these things are vectors. There's nothing wrong, hopefully, there's nothing wrong with saying, hey, that plane was traveling at 275 meters per second southwest. That means Southwest Airlines. That was a horrible joke, sorry. So there's nothing wrong with saying, well, this is how fast and in what direction. Nothing wrong with saying that. So I want you to do this. Choose a scale. Now here is a number. So 1 centimeter equals some number of, and in here goes units. Right? Like here I did some number of units. So come up with a scale for each of these that makes sense. My only request is that you don't do 1 centimeter equals 275 meters per second and then just draw a 1 centimeter long vector. All right? You're gaming the system. The goal should be to make it fill up a good amount of space. All right? Pick a directional orientation. You tell me which ways, since here we're working in a cardinal direction thing, you just define which way is north. And it doesn't have to be the same direction here as it does here. If you want to make north upward over here and to the right over here, then fine. You do what you want. Doesn't make it more right. All right, so that's a U. Oops. You'll have this done when you walk in. Now, vector sums. Scalars can be added. Right, like, it took, you spent 20 minutes on one, homework assignment, and you spent 60 minutes on another homework assignment. You spent a total of 80 minutes on your homework. Sure, no problem, right? Vectors can also be added, but it's definitely not always quite as simple. All right, so for example, let's say you're walking, how fast do people walk? Well, people walk really about 1 meter per second. I'm one of these people movers at the airport. You know what I'm talking about? Conveyor belt, for lack of a better word. But that thing has its own speed relative to the floor around it of, say, 1.5 meters per second. Well, how fast do you end up walking? Well, maybe this is a duh, but you end up walking 2.5 meters per second. All right, well, now let's say over here, you walk in the wrong direction up the people mover. What's the magnitude of your resultant velocity? Holy cow. So what's the size of your resultant total velocity? Well, speed, but with direction associated with it. There's a better definition for velocity. We'll get there in a couple weeks. But here's some code words. Magnitude, right? We know that means size. Resultant is a word that means total. Resulting, it means sum, really, especially for vectors. And velocity, you've heard of that, but it's not just the same thing as speed, because it has direction associated with it. Meaning velocity is a vector. There's a hint for page 1. Right? Well, maybe this is a duh also, but you have the people mover going 1.5 meters per second, but you walk the wrong way still at 1 meter per second. Well, you're going to end up going 0.5 meters per second. So we could probably do those simple ones without much, maybe without thinking a whole lot. Now, the thing I should make sure I'm still saying is 2.5. How fast you end up walking? Sure, 2.5 meters per second. Here, let's make sure we're doing this direction part. So we're still 0.5 meters per second in the direction of the people mover. Right, so in one case, notice we added the magnitudes of the velocities. Here, we ended up subtracting one velocity from another, or subtracting the magnitudes, I should say. All right, so how do you know whether to add or subtract? Well, we'll show you one more example. Now, I think yours might be in a different order than this. This is a U. Okay, you go. You got 2 hyenas pulling on a wildebeest carcass. You know, why not? One pulls with 50 pounds, the other pulls with 75 pounds. What's the biggest total force they can exert? And sketch it. Here's the wildebeest carcass. If you're an artist, congratulations. That's fair enough. What's the smallest total force? Oh, wait a minute. Oh. Pulling in a certain direction. Okay. Maybe that helps you out with one of your other assignments. Here's your wildebeest carcass. Draw me 2 of these cases. One in which the hyenas end up with the biggest total force, and one in which the hyenas pull with the smallest total force. Got it? Good. Oh, better. So, now, let's go back to our people mover. Right? People mover, let's say, runs this way. And I can use this vector to represent the 1.5 meter per second velocity of the people mover. How fast the people mover goes and in what direction. Right? There's a velocity vector. It says 1.5 meters per second. Now, the spider walks across the mover at a speed of, I don't know, how fast is your average spider move? This is a quick one, I guess. We'll call it 0.6, if you care about sig figs, meters per second. Across. Now, I'm not going to use a ruler I'm not going to make a scale here, but if that's 1.5, then, there's 0.75. 0.6 is about, I don't know, let's just sort of sketch it and say there's our spider velocity that looks like that. So what's the spider's resultant velocity? What's the spider's total, overall speed with the direction associated with it? Well, now what I should also say, if I'm doing this right, is I should say relative to the floor under the people mover. All right, so what we do here is the spider does end up, going this way at 1.5 meters per second. The spider also does end up going this way at 0.60 meters per second. So it doesn't end up that the spider ends up going 2.1 meters per second. It would if the spider was going this way. Oops, come here. Right? And look, we could actually, if we put those two vectors like that, we would end up with, almost one vector that is 2.1 meters per second. But the spider's not going that way. And it's not 0.9 meters per second in the direction of the people mover, but it would be if the spider were going this way, and we could put the vectors like this. And notice, as long as I have the tail of the 0.6 touching the tip of the 1.5, we could, end up with our 0.9 that goes from, I'm going to get in trouble with, our 0.9 would look like that, but that's not the direction that the spider's going. All right, so see you later. So, well, remember, we said as long as the tail of this one touches the tip of that one, well, that's actually what's happening. And the representation of the spider's actual velocity is this. The spider does go 1.5 meters per second north. At the same time, it goes 0.60 meters per second, did I say north? Whatever, in the direction of the people mover, and 0.60 meters per second across. And the resultant of that, the sum of those two velocities, the total, the net velocity, this thing's resultant velocity, I'm saying the same thing as many different ways as I can, is this. This is the spider's velocity. So how big is that? We've got a couple options here. If you wanted to use a ruler, you could draw that, pick a scale, draw those vectors to scale, and then measure how long the green one is, and then use your scale and figure out, well, what's that length of that vector actually represent? Or most of you are slick enough to use some geometrical tools to find what I'm going to call VR, V resultant. All right, so what I'd like you to do is option 1, draw to scale and find VR, the size of VR. Option 2 is use geometry to find the size, the magnitude of VR. Okay? Now, what we want you to do also is find this angle theta. Because when we say velocity, we don't just mean speed. Speed's just how fast. Velocity's kind of like speed, but the direction also matters a lot. So we want to know what that angle is. Okay? And you have two options to do that. You do this. You could draw it to scale and then use a protractor. Or you can use geometry and trig. But one way or another, I want you to find two things. The magnitude of the resultant velocity. And we can do that like this. Magnitude of, absolute value of. And then I want you to find theta. But you see that it's not 2.1. It's not 0.9. It's something in between. Find it. Good? Good. Yeah. So these examples about wildebeests and spiders and people movers and airports are examples of what we call vector addition, or finding vector sums, or resultant vectors. And it doesn't matter what kind of vector we're talking about. Here we're talking about velocities. Here we're talking about forces. Here, earlier, we're talking, well, yeah, that's all we're talking about. But in the activity that you did, the walk this way activity, we were doing dealing with changes in position. So it doesn't matter what kind of vectors we're talking about. If we want to find a resultant, you always do it the same way. All right? And if we want to find, well, the sum of vectors A and B, we want to find, vector C that's equal to the sum of vectors A and vectors B. Well, vectors A and B. What you have to do is, well, you might have to move one of them. You can't do it if they're just looking at them like this, but if we move one of them so that the tail of it touches the tip of the other, well, now we can find the resultant vector. Here, oops, there is vector C. Now, coincidence that it happens to go straight up. I wish I hadn't, it's not always going to work out so nicely. All right, but if you ever want to add two vectors, like we just added A and B, what you have to do is add them tip to tail. All right, notice here's a tip, here's a tail. And what's nice is it doesn't matter the order that you do it in. You can add things in whatever order you want. That's called the commutative property of, the commutative property of addition. Right? And notice if we did B first and then A, well, we get that vector C. Same vector? Sure it is. It happens to be over here instead of over here. But it's the same size and the same direction, right? So it's the same vector. If you're doing this, really carefully, you'll use a ruler and a protractor. If you're if you're sketching, that's okay too. This is a U. Draw. You could sketch if you want to use. If you're a detail person and you want to make sure you use a ruler and a protractor, be my guest. If you want to sketch and sketch carefully and not be a spaz, be my guest. All right. Just make sure and ask yourself: are they drawn tip to tail? These definitely are not. Of these, one is and one isn't. So just be careful when you're trying to draw. No, you're trying to draw the resultant vector in each case. Okay. We'll talk about this tomorrow when you get here. I'm sorry, you people that are in my class, you'll see this next time I see you, and then we'll get to the harder stuff. Okay. A little longer of a video than I'd like, but there's number one, folks, for the year. See you soon. Oh, I didn't think I stopped it.